Cool. So, welcome to this video. We are going to continue with where we left in part 1. So, part 1, we wrote the initialization function, and also we wrote the pin mode, the function to set the pin mode. So, one little bug I realized in the pin mode is that when I'm setting the value for the pin, I was using the pin number. Instead, I should be using P. It should always be between 0 and 8, right? Between 0 and 0 and 7, ideally. 0 and 7. Yeah, so in this video we are going to write the next function, which is digital write. We write digital write function. So it's a void, and then MCP23017 digital write. It expects the pin and the level, right? So we want to pass uint ht pin and uint ht the level, right? Okay, so what we need to do here, we need to resolve, just like the other one, resolve which ports we are using, and therefore we'll resolve which register to use. Next thing we do is read. That is check the pin number, right? Then we need to read from the register, from the port register. The other thing we need to do is modify our pin. Then we write back to the register, right? So resolve which port register is basic. It's just like the other, just like this CP. These other let me open main.cpp MCP. I want to duplicate it. MCP, yeah, like that. So that I just use these functions that are right here on the pin mode, because we'll be sharing a lot of them. So we want to resolve which register are we using. So first of all, we need to check the data sheet. Whenever we are writing to the GPIO, we use the register that is called the output latch register, OLAT, right? And it says here that the OLAT register provides access to the output latches. So a read from this register results in a read of the OLAT and not the port, right? So get that right, not the port. And then a write, this register modifies the output latches, that modifies the pins configured as outputs. So this is our register of address, our register of interest. This is our register of interest. It is used to set either logic high or logic low, right? So we already have defined the OLAT address here. So you want to check if the pin that has been passed is less than 8, it means we in bank A, which means we'll use this OLAT A. If the pin that has bin passed is more than 7, we are in port B. We use this, right? Right. So let's do that. So the first thing we do is we define some local variables here. For example, the register. We define init 80 register value, and we define the pin D, right? So reg will be condition ternary operator. We check can be either OLAT A or OLAT B, output latch B or output latch A. So it is output latch A if the pin that has been passed is less than 8. Otherwise, it's output latch B. Right? Register value is the value that is read from the port register. P is 0, should be between 0 and 7. Right? of 0 and 8, 8 not included. Again, mod operator, so pin odd 8. Right, so this is checking the pin number. Then we read from the port register. So we say here, because now we have a register address, we need to check what is the already existing value. The reason why we are reading from the port register is so that we don't change other pins. So some other pins might be running an LED or a button or whatever. They might be input, output, but we don't want to modify that. We want to modify only a single pin. So we need to sample the register, get it back, change that specific pin, then write it back. Okay, so first of all, we begin transmission here. So we are reading from this device address. This device address, we don't know the frequency, right? So the next thing we do is we write the register address. So wire dot write register, right? This value there. Then we end transmission with a false, which means that the bus expects another byte that contains, or rather that has a command. So for example, in this case, we request from this address, we request 1 byte of data, right? So the byte that we have read, we put it in the value variable. So this will be wire dot read. Again, as I said in the last video, that request from just takes that, samples that byte, puts it in an I2C buffer, but does not read into your program and into your code. So read is the one that copies from the temporary buffer to your register value. That's why we have these two commands right there. So the thing is that for I2C and Arduino ESP devices, the reading is very strict for some reason, right? So the next thing we modify our pin. So this is digital, right? So the pin can be either high or low. So from the data sheet, you have seen that logic high is a 1, logic low is a 0. No brainer about that. So we modify that pin. So if we check the level that was passed, if the user wants to set as input, as a low, low is 0, right? So we clear the bit. So which bit are we clearing? We are clearing the pin number P, right? This one from this register, or rather on this register value. So you want to say reg value is equal to, we clear bit with and the bitwise not 2's complement with a mask of 1 shifted into what? Shifted into the pin that you want, that way. Then we say else if level is equal to high. What you want to do is say reg value is clear that bit. Now we set that bit, sorry. Set the bit. So we set it 1. So we do 1 mask P, like that. Then we write back. So at this point, we have our modified register. Then we write it back by saying, this is the same procedure here. So I'll just copy this, copy that. I don't want to type a lot. So this device address, reg value, that's fine. So this should be able to work, right? This should be able to work. So if we try run this code, we should be able to light an LED. Okay. But first, we need to write that code here. So we need the expander. I need expander. And we 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 need And then here we set pin mode as an output for an LED, for example. And then we set a right high, right? So we want to say expander dot pin mode, just pin 0 of bank A, mode is output. So output is internally defined macro. So it's normally as it's an internally defined macro. It expands to this decimal value, which is a 1, okay, or a 0, depends. So expander dot digital right in 0 may actually define. Let me use this macro, this definition of a pin: LED 0 and LED 0 here related high at that. So fingers crossed it runs the code and writes the LED high, right? If it doesn't, we'll debug. Okay, so let's upload that. Let's PIO run -t upload. So I've connected my LED to pin 0 GPIO. Oop, I didn't close the serial monitor, I think. Close. Then upload this. Right? So P0 is connected. I'm just checking the hardware. It's pretty basic. Should run nicely. Okay. Let's see. It's actually it's lighting up the other devices. P0. Okay. Let's write them. Let me reset. Let me write a reset function. Fuck. Then write a reset function. So right here I can say void MCP23017 is set. So we should expect a reset the pin at which the reset pin is connected at. Right? So we just wanna say check now if okay, this one for now we will change this later, but you don't need to write a lot of code. We can just say reset pin. Reset pin. Pin we say low. That way. So I copy this and update the driver signature here. Okay, so in my main, so the reason why I'm doing this is that the I2C device, if you can see, it has lit like other LEDs that are connected. It means that it has like a previous state. So I need to clear that state first, so that I show you that that specific LED that we have written for is the one that is lighting, right? Here's LED 0. Okay, so we reset. Let me just reset it. Then say expander dot reset. Let's reset which pin. So let me say reset pin and connect that pin to something. Fine. Set. Let me use pin 5. And I'll connect it with a jumper cable to reset pin. See whether it works. Pin 5 of ESP. Let me upload the code. Load. Where is my? Yeah. There are these warnings. Okay, we will change them. Wait. See whether it resets. Okay. And still does not. So what I'll do, I'll just remove these other pins and remain with only P0. I'll remain with P0 only. I'll remain with P0 only. P0. So real quick, connect that to P0. Okay. Let me write it low and see whether it works first. Output low. Okay. Output and low. That should be able to work. Oh. Let's see this device. Okay, there's an error. Bus already started in master mode. So means there's somewhere else I'm starting it in master mode, which should not be the case. Let's check the CPP. Begin transmit. Okay. This is where the problem is. Because I've already called the begin. So here, I should just say the begin transmission. Right? Yeah, should say begin transmission. Because I've called the ESP as our master device, the others should be slaves. Okay, so load. We check the serial monitor. Okay. Let's see whether that works. All right, that works fine. It turns it off. So if you can, let me show you. This is the LED of interest. I don't know whether you'll be able to see. This is the LED of interest. There's an orange LED here. Right now it's off. I'm going to upload that code. Oh, no. I'm going to change that. Write it high. Let me comment this out. Write it high, right? Let me write it high. And then upload it. So if it works, we should see that LED, an orange LED here, right? Lighting. Right. Let's see. Nice. So you can see that LED right there. Let's try something else. Let's try to blink it with like an unblocking delay, right? So pretty basic. You just write static queue int. Static unsigned long last millis, right? Then you say if current millis minus last millis is greater than, let's say 300 milliseconds, right? 300 milliseconds. and just put this in like 2. If it's then we have LED state is equal to, we toggle it. So LED state is nothing but a bool variable here that starts as a force, and then we update the last millis is equal to the current time, current millis, right? So first, okay, what we need to do here now is update this guy here with digital, right? The LED state, right? True or false. True is a 1, false is a 0. All right, so let's see how that works. So again, this is LED, right? Right now it's let's know it's on. Let's see whether it blinks. Uploading. Nice. So you can see it's blinking, which means that like our 2 functions are running as expected very nicely. So that's 300 milliseconds blink, right? Okay, so that's pretty basic. Pin mode and digital, right? The basic driver stuff. Now, that's output. Let's assume we want to read our switch, our push button. How do we do that? So obviously we set the pin mode as an input, which we already have, and then we digital read a pin. Then you operate on that. So let's write that function really quick. I'm just gonna put that right there and implement the digital read function. So this is a function. Oh, let me make sure I'm still recording this thing. Oh yeah, it's cool. Okay, everything's fine. Cool. So implement this here. I implement it right here. So it's a void MCP23017 digital read. Yeah. We expect a pin that we need to read from. So which pin are we reading from? Oh, it's expecting a uint8, sorry. The return type is uint8t. Cool. So again, the logic is very simple. We check whether we resolve the port and pin, right? We sample the existing register value. Should we usually sample it? We are not modifying it, you're just reading it. No, let's say we read the existing. Then we use a read here. Read the existing. Then the next important thing is we extract the bit. Extract the bit of interest. Then we return the bits. Like, very simple. So obviously, normally, or rather as usual, we have the register. You have uint 80 fetch value. This driver is very easy because the register bit width is just 8, so you don't have a lot of complicated bit shifting stuff. But maybe in our next video, I'll write another driver that uses, for example, 32-bit registers or 16-bit, or has multiple bytes that we need to read. For example, the MPU 6050 has a very nice register map or something else, right? Anyway, so the most important thing is just to get the thing working. It doesn't matter how the registers are addressed. If you get it working, it gets to do the job you want it to do for you. That's the whole point anyway. Plus, this code is, you write once, probably you forget about it. You just be using it. That's the good thing about embedded. You just set some pin sets of registers and save it, forget about it. You'll always be using it, right? Now, it doesn't change very fast. Okay. Right, let's go on. So reg value, and then you int 80, it is a pin P, right? So resolve a port and pin. Again, you'll say P is equal to, no, we say the reg is equal to, if pin is less than 8, pin is less than 8, we want to say, what are we reading, right? Which is the register that we are reading. Data sheet comes into play there. So the GPIO reflects the value of the port. So reading is register reads the port. That's all we need. GPIO A or GPIO B. Okay. So read the existing register value. So we say wire dot begin transmission. The address is this device address, right? Then we say wire dot write. Which register are we reading? So we write the register value, register address, not the value, sorry. Then we end transmission with a false. We request the bus to give us the value of the GPIO address. So you say wire dot request from. You're requesting from the address. Requesting from the address, you confirm that which this device address. Device address 1 byte. And we end the transmission. Now we read it. We say now reg value. Reg value is equal to wire dot read. So we read that and then we can end the transmission or not. Okay, wire dot end. Let's see whether it will work. End transmission. True. Right? So here in this code, we have access to the register, the current value of the register. So we want to extract that specific pin that we want to read, right? So what we want to do is look back our pin. So P is equal to pin mod 8, right? Now, here's where it gets interesting. We want to extract a single bit. We need to, when you're extracting bits in low level, you use an AND operator. So we know that, I'll just try to explain this as easily as I can. 0, 0 is a 0, right? 0, 1, what? 0, 1 is a 1. 1, 0 is a 1. No, it's a 0. 0. 1, 1 is a 1. So this is the AND operation, right? So it means if we shift a 1 into a point, into our position of interest and AND it with the register value, we'll get a 1 if that bit is set, and a 0 if it's not set. Very basic, right? So what we do is say register value. Reg value is equal to, let me go systematically here. Let me see your print. The best way to explain this is to just show it. Serial print len. The register value in binary. Right? Binary. So upload this. Let's upload this and see how it works. Oh, no, I think I didn't call it. Let me call it first. So here, I'll just say expander dot digital read 0. Let me read the bit 7 of port A. So it should print that. Let's see. Let's upload and see what it prints. So right now I've not connected anything to pin 7. Pin 7 is not connected to anything. Like me. Wait. Get throw something right here. Okay. So open the serial monitor and we check. Oops. There's some very big problem. Okay. I know where the problem is. So in our main, let's return. We are not returning anything. Let's return this. Return reg value. Let's not print here. Remove that and print it here. So we print this. Just say byte x is equal to, oops, byte val is equal to that. So print val, print it here as a binary. Let's see whether that like does not pose a reason on the ESP. Loading. Serial monitor should be closed. Uploading. Okay, let's hope that this thing works. Nice, cool. So I don't know whether you can see this clearly, but so let me open it. Let me open it here. Just say PIO device monitor. Baud is 115,200. Yeah, nice. So if you look clearly, you see the last bit, the first, the LSB is, this is LSB is P0, right? P0 is toggling at the rate of 0, the rate of 300 milliseconds, right? This is LS, this is P0, P1, P2. Now I'm interested in P7, right? So the reason why it's printing 3 values or 3 bits is because all the other bits from this point onwards are 0, right? So they're just 0, 0, these are 3, so 1, 2, 3, 4, 1, 2, 1, 1, 1. So the one is the one that is toggling between 0 and 1. So because all of these others are 0, there's no need of printing it. So it just discards them and print the last 3. Now if I set this to 1, if I connect this to a high and I read it, should be able to print something like this, right? So let's test that. I have a push button here, push button that is connected to a high, just connected to, it's pulled high basically. So I'm going to connect it to P7 and not press it, and we see what happens. So P7, nice. So connected it, nothing changed on the hardware, but on the software side, you can see now the new value that is being printed. This value is set, right? So the way I've connected this pin, if I press it, they should pull the pin low. Should pull that pin low. So if I press this push button, see that response time is not like a lot, but it's showing the response time, right? So if you press it, it becomes a 0. If you release it, becomes a 1. Nice. So it means our digital read is working perfectly as expected. Okay, so I'm gonna close this monitor, and now we need to extract this bit. We don't want to return this whole. We are not interested in the other bit values. We just want this last one, right? This last one. So how do you do that? It's a very basic operation. We say val, let's say unit ht val is equal to, we right shift, okay, right shift reg value by the number of pins, then we extract that specific pin. So reg value, we right shift it by t, and we AND it with a 1. So what this will do, it will put the, so if we're interested in this one, and this is bit 7, so you will left shift this value by bit 7. 1, 2, 3, 4, 5, 6, 7. It means we will discard all of this. We remain with something that looks like this. All the others are 0. Then we AND it with a 1, which is basically, okay, now depending on our code, this is a, what is a code? Is a 0x01, right? So it means down here you'll have 0, 0, 0, like that. You AND that, you're bound to get a 1, basically. You get a 0x1. Simple. Let's say a user passed, or rather the user was interested in bit 2, for example. No, bit 1, sorry, this bit. What do we need to do? So this is bit 1, right? Again, to extract that bit, we shift. This is the register value. We shift this right by 1 bit. So once we shift it, it becomes, we discard that, it becomes 0. We append a 0 here, then we start all of that. Put it right there, like that. This is that way. So basically what this does is that it makes this a bit of interest as the last one. It puts this as the last one. Then we AND it. AND with 1. We grab it for 1. Basically that will give you a 1. You ask, because all of these will be zeros. You AND it with a 1, it will be a 1. If it's a 0, it will give you a 0. Simple. So this is the operation we write right here. This is that operation. And you need to return now, instead of returning the register value, return the val. Return the val. Yep. So that's that. Let's check now. Now our test code. Let's say V is digital read pin 7. So if it's pressed, it's going to 0. So we need to return a 1 if it's pressed. So we negate that and check it here. So if V, can say now here, if V, right? It means the button was pressed. Serial println button pressed. Else serial.println button not pressed. You don't even have to print it. You can just leave it not pressed because you're interested in when it's pressed. Okay, it depends on on your application. So I'm gonna upload this to the USB and see whether it works. Cool. So I'm gonna open the serial monitor again and short pressed. Right. So let's try pressing it. So here it is. I press. See that? Press and hold. Release. Press and hold. Release. Release. Boop. So this button is not debounced. So you might get some false readings, but ideally you can see that it's working very nicely. Right. I think I'm gonna call it a video there. And one thing you notice about this code, there's a lot of repetition, right? We are doing all these checks. These checks can be like put in their own functions. See, this is repeated, this is repeated, this is repeated. So it's not optimized, but it works, right? So I will not optimize it later, put them in their different functions. But at this point, I'm really happy at what we have written so far. So the code, I'll link it in the description so that if you want to check it, you can easily check it, right? Plus, you can also test if you ever get this device, you can also test other ports to see whether the looping works and whatnot. But I'm confident that it is all right. So yeah, that's how you write a basic driver in I2C ESP Arduino framework. Maybe I'll make another video for maybe STM or another microcontroller. And yeah, if you don't write it, you can always find someone who has written it and like use it, consume it in your code, which is totally fine. If the project is like the timelines are playing around with you, you can always do that instead of writing it from scratch. But writing it from scratch helps you really understand intuitively what is happening behind the scenes, and I prefer to do that. Unless something is really, really advanced, you don't want to like waste your time, trying to write it. So you just consume whatever is there. But all right, let's end it there. If you have any question, let me know. You can put it in the comments. You can contact me. There's no problem. And yeah, see you next time.